Okay, hi everybody. Very nice to welcome you all to this next seminar from the IAVC Commission on Volcanic and Igneous Plumbing Systems. You're all very welcome. So I just wanted to say a few words at the start just to introduce our commission, as some of you might be new to our events. So the aim of the commission is to provide a forum for VIPS research, which goes beyond disciplinary or methodological boundaries, and to foster an integrated understanding of magma transport and storage in the crust. I'll just introduce you all to our committee, and some of the committee have their videos on, I think, so you can wave and say hello as well. So we have, I'm the current president. Katrin Annen is looking at equality, diversity, inclusion in the committee. She's also our vice president. We have Luca and Chiara, who are looking at events. We have Steffi, who is one of our co-founders and committee member. Corinne, who's our ECR representative. Then we have our blog team, Paula, Caitlin, and Keris. And we also have our website and social media team, Gabrielle, Chelsea, and Andres in Colombia. So if you want to get in touch at any point over the next few months, or about any events that you think that the Commission should get involved with, and we're also creating a new form where anybody that's interested in convening a session at upcoming conferences can sign up. So look out for notification for us about that. But basically you can get in touch with us in different ways through our website, through our Discord channel, and we have a Discord channel operating today for this chat, for the seminar. And also, as you saw when you joined, this seminar is being streamed to YouTube. So a couple of guidelines for the audience. The talk will be about 40 minutes long. Please keep your cameras and your microphones off during the entire presentation. The talk is being recorded and live streamed to YouTube, so you'll be able to look at it afterwards if you like. We'll take questions at the end. You can ask your questions, we don't have a time limit for that, so it just depends on how long Sam can take it, really. And how we go. To ask a question, you can just put an X in the chat, and then we will ask you to formulate your question. Otherwise, you can type your question in the chat and we'll read it to Sam on your behalf. We also can take questions in Discord and in YouTube as well. So lots of different ways to interact during the seminar. Okay, so I'll hand over to Luca, who's going to introduce our speaker.
Thank you very much, Janine. I would actually like to say that all this event was organized thanks to Chiara more than me. I was a bit useless in the last couple of weeks. So thanks a lot, Chiara, for doing this by yourself, and thanks, Sam, for agreeing to participate to this. Sam is gonna touch on a very important subject, I think, because it's how do we reconcile model and geology? I think this is one of the fundamental questions that we have to address when thinking about models. So Sam studies how magma-induced structural deformation of planetary crust affects volcanic activity. He uses a mixture of geological field observation, laboratory and numerical modeling, geochemical analysis, and remote sensing of Earth, the Moon, and Mars. He's a Fulbright BAEF alumnus. What does it mean, Sam? BAEF?
Belgian American Educational Foundation.
Excellent, thank you very much. He has received grants from the Vocatio Foundation and the Science Communication Year Prize from the Flemish Royal Academy of Belgium that supported his passion of combining volcanology and science communication. At present, he is leading the Demo Planet project at the Mars Exploration Laboratory of the Space Research Center of the Polish Academy of Science in Warsaw. It's really a pleasure to have you here, Sam. We are really looking forward to your talk. I've just made the introduction, and then Chiara is going to moderate the questions at the end of your talk. So thanks again for being here, Sam.
Okay, thank you very much. I will share my screen, and then hopefully you can see that. Yep, is that good? Okay, great. Thanks a lot, Luca, for the introduction, and of course to the whole commission for inviting me. I'm aware of big shoes to fill after John Blundy's talk and Eleonora's talk, so I hope I'll be able to entertain you in the next 40 minutes or so, I've been told. So how can we reconcile models with geology? It's a question I've been asking myself probably for the past 10 years. And at the end of the presentation, the question mark will probably remain as the one major thing on the screen. But I hope to take you on a train of thought today about deformation modes induced by magma intrusion in planetary crust. And hopefully my presentation can serve as an interesting starting point of a discussion afterwards, which is my major aim, I guess, more than presenting my own or others' work today, to have this interesting discussion. So before going forward, my ideas and research I'm showing today are really indebted to all of those institutions in Brussels, USA, and now in Poland that I have been and working at, and all of those foundations who have supported me over the years by different means. And of course, everything I'm talking about today is a product of collaboration with many people, names you see at the bottom here, but definitely collaboration and discussion with many more people. Many of you are here today. So I'm indebted to them and you all, definitely. And last, before we go on, those two little ones are here to remind you that if you have those blue and red stereo glasses, this is your moment to go and run for it, because later in the presentation, we will there will be 2 slides with 3D stereo images you can view through these glasses, if hopefully it will work on your screen. So if you find them, go for them, and then let's kick this off. So at most of the talks I'm starting recently, I'm trying to remind myself and anyone listening the major question, or one of the major questions we try to answer in volcanology. There have been several events, as any year, where volcanoes have surprised us, like on Iceland, where indicators of magma on the move were present, but the actual moment, the actual location where finally an eruption started earlier this year was a bit of a surprise to the local scientists monitoring the situation as well. And the same on La Palma. Involcan definitely knew something was brewing below Cumbre Vieja, but then finally the exact moment, the exact location is still a bit of a surprise, even if everyone is in a higher state of alert. So we really still have a lot of work to do to answer this basic fundamental question: how does magma in place and how does it move in the crust before it erupts? And how can we better constrain that moment of rupture at the surface? And one way of understanding pre-eruptive conditions at La Palma was by those new streams of data we have using the Sentinel images, Sentinel satellites, for example. You see 2 interferograms here. So these are ground deformation maps where the colorful fringes show you displacement. The closer they are together, the higher the displacement, the deformation actually is. We can use GPS stations to measure that ground deformation as well. And then we go on and apply analytical models, inversion models to that ground deformation data and come up with a model of how we think that magma intrusion might look like. How does the opening of that magma field fracture look like? How much magma do we think is below the surface? How deep is it, etc.? And all of this is done quite quickly. We get the images, we have pipelines, protocols for quick data processing and quick models that can give you this kind of answer within a matter of minutes to hours, if you're up to the task in that moment. But very often, we tend to forget in those moments of crisis, when things have to go fast, that in volcanology, we're really acting on multiple fronts. And so we have our volcano with many processes going on, eruptive processes, but also, and we're all aware of that as members or supporters of the VIPS Commission, also what is going on below the surface. And we have multiple fronts where we try to understand what's going on, especially below the surface, where we cannot directly observe magma propagation processes. We just can't. So we use lab experiments, we use larger field experiments, community workshops, etc., but also observations from the geological record, petrology, geochemistry, and then really exciting new developments in numerical modeling, artificial intelligence, machine and deep learning, and bring all of that really together to try to understand what's going on and below the volcanoes as an input to hazard models and mitigation plans, because that's the final aim, of course. And this is a synthesis figure we have put together for review for a bulletin of volcanology that I will come back on later. So I have a feeling that we tend to sometimes forget how complex the image really is and how complex the solutions to our questions sometimes have to be. Hence my title of today. And in today's talk, I will try to look at those 4 questions here. First of all, look at magma intrusion modeling, which assumptions guide our models, and then get back to geology. What does geology really tell us, and are we staying true to our observations? And then use a bit of my own work to discuss how we might be able to combine analog and numerical models to help solve our main question on magma emplacement. And then finally, how we can reconcile our models with geology. So which assumptions guide magma intrusion modeling? And I'm pretty sure at least some in the audience will say, oh yeah, there we go again. Yes, when we have surface displacement measured at a volcano as an indicator of magma that is on the move, that is pressurizing the volcano from below, we can, as I said before, measure that using satellite monitoring, GPS stations on the ground, and we pump all of that into analytical numerical models, trying to estimate the characteristics of that magmatic source. And those question marks here indicate that we have a major question to solve, that is what happens between the magma intrusion and the surface. And the most broadly used, but also most simple models are those that assume that that volcano or the shallow crust will deform elastically. Why is that? Because assuming elastic deformation, linearly elastic deformation, means that we assume all of that deformation caused by the magma is recoverable. Take the source away and the whole stroke can return to its initial state. That is the mechanical definition of elastic deformation. And the reason why it is used in fast analytical tools is because it allows for a straightforward mathematical solution, which I will not bother anyone with right now, but it is the most straightforward, fast way to describe the deformation. And then we have different magma source geometries we can use. And here is an adaptation of a figure made by Sigmundsson and colleagues for Steffi Burgert's VIPS book, where we have those different sources that can be used. The MOGI source is the known most simple one. It's a pressure point source, the black dot on the lower left in the diagram that pressurizes equally in all directions. And the result at the surface on those colorful maps is a dome-shaped uplift with a maximum uplift in the center. We can then use a variation on that, a McTeague source, which is a pressurized spherical cavity, but also can use a spheroid, and that allows for a bit more playing with that geometry of the source, and then allows for modeling asymmetric, but still dome-shaped uplifts or surface displacements. And then we move to Okada sources. These are rectangular dislocations, so a rectangle buried in the subsurface that pressurizes perpendicular to its plane. And if that is a vertical rectangle, we'll get a very typical butterfly-shaped surface uplift, while if that is a horizontal sill, we get rather a dome-shaped uplift that is similar to the one yielding from the MOGI source. But of course, because it's a rectangle, we have a rather box-like, square-like layout of that surface uplift. So if you look at magma sheets at those rectangular dislocations, I am displaying here two quick and dirty forward models after Okada, using a variation on the D models code of Maurizio Battaglia. That is a code that is used very often nowadays in volcano monitoring operations, in automatic tools, trying to get a first quick and dirty estimate of a magma intrusion, of the source of deformation that is observed at volcanoes. And so at the top, you see that flat-lying intrusion creating a dome-shaped uplift. At the bottom, you get this typical bulges and trough shaped uplift with a depression above the apex of the vertical intrusion, and then two bulge-shaped uplifts on either sides of that. And so really, so what is going on between that simplistic intrusion source and the surface? Well, there are a few drawbacks to these models. First of all, these are static models. We simply model the one circumstance that answers to the data we have observed at the surface. We are only able to model simple intrusion geometries, and that medium where the question marks are is assumed homogeneous and of a linear rheology, if you want. So, so these are drawbacks, as I will show later, that geology asks for more. And one way of solving complexities is, of course, and we all know there's been a whole range of exciting developments in intrusion modeling recently. And one of the ways is combine different data streams. This is an example of the Bardarbunga 2014 eruption, where, or intrusion, I should say, where this colorful map is again an interferogram from radar satellite data, where the colorful fringes show that displacement in this typical butterfly-shaped pattern. But if we combine this and GPS observations on the ground, but also locations of seismicity in the subsurface, and in the lower left diagram, these are the black dots, then we can do joint inversions and get a much more accurate view of or idea of the intrusion. And on top of that, this particular inversion uses distributed opening. So you divide your one large rectangle in smaller rectangles that each can have their own opening. And in this way, we can get a better idea of the opening and the complexity of the geometry, but we can also allow for time-dependent monitoring and repetitive inversion to kind of follow the development and the evolution, the propagation of the magma sheet. And then on the right side, you see the surface uplift, the surface deformation that indeed followed, in this case, this typical butterfly-shaped and bulges and trough pattern deformation with the central trough and bulges on the side. But again, the question is, what really happens between the magma intrusion and the surface, and do we model that actually right? And another even more exciting, I would think, recent development, of course, is the application of machine learning, deep learning, artificial intelligence, where it now becomes possible to have continuously updated databases of volcano deformation data, so process satellite interferograms scanned continuously by those algorithms and try to detect in real time magmatic deformation signals. And in this case, this example by Matt Gaddis and others from an Earth Archive preprint even classifies that deformation as more likely a dike or more likely a sill. The danger in those applications then lies in simply taking the results as they are and moving forward, without asking ourselves what the processes are that drive that magma emplacement in detail. So let's look at the theory of magma propagation. Field observations in the past, in the 70s, 80s, have driven this mode 1 opening mode deformation theory, where you have where the dike is or the magma sheet is a hydraulic fracture with a sharp sheet tip, a taper body with a closing tail, a tip cavity ahead of that pointy tip, and the host rock deforms linearly elastically. So you see bending there in a diagram, and you see that above the apex of the sheet intrusion, you get extension, you get normal faults forming that translate into the formation of a graben or a depression above the sheet intrusion at the surface and those two uplifted bulges on the side. And this assumption is taken as the main driving physical law, let's say, for developing most of the nowadays operationally used models. I'm not going to explain much more about it, simply because Eleonora did a better job than I could ever do. So she explains more of the details of the physics behind opening mode deformation in her previous VIPS webinar. So go ahead and look at that. Eleonora kindly used that time so I can free it up now to talk about the other aspect, the other end member, let's say, which is shear mode deformation. In this case, magma intrusions are seen as viscous indenters with a blunt sheet tip. The fracture walls are rather parallel, so there's no tapering, no tail at the end, really. And the host deformation is plastic and focused ahead of that propagating tip. See it a bit as a bulldozer, just pushing through the rock instead of a sharp knife like mode 1 deformation sees it. And this has been postulated by using analog models like Lucie Mathieu did in the past, but also by detailed documentation of geological observations by Spakapan and others. So we have those two seemingly competing end member styles of propagation, and maybe in the past we have been too much entrenched, let's say, in our own worldviews. Eleonora wrote a review in 2015 that was called Schools of Thought, exactly to highlight that. And I hope with geology, we can try to find a way to think differently about all of that. And today I obviously want to make a case, just like Peter Jackson is doing recently, but get back to geology. So let's try to do that. First of all, if thinking about mode 1 propagation, all of us know these images of dikes and sills, knife-sharp magma sheets that just cross-cut through any sequence of rock. This is a picture I took on Moeli, one of the Comorian islands, but you all know definitely the pictures of dikes cross-cutting whole sequences of basaltic flows, breccias, tuffs, whatever you want, on Iceland, for example, without seemingly much consideration for its surrounding host rock. It just broke it apart and moved on like a knife indeed. And Eleonora has showed good examples of that as well. So on the other hand, recently several outcrops have been described in detail, like this one here in the Neuquén in Argentina, originally by Spacapan in a 2017 paper, but this specific image from colleagues Bertelsen and Olivier Galland's group of this year. So here we have more blunt fingers, sills of andesitic intrusions, which have completely sheared, imbricated sequences of limestones and shales. So it's probably difficult to discuss that these are not clear indicators of shear mode deformation. So this is an extreme end member, let's say. But there are other cases where the circumstances are more complex and more difficult to understand. And we focused in my PhD on one case study in the Oslo Rift on Hovedøy Island. It's a small island in the Oslo Fjord, just outside of Oslo's downtown, where you have literally tens of segments of thin dikelets, few centimeters thick, and placed in a sequence of shales and mudstones. And we documented in detail the geometry of those different tips and saw that we actually have a spectrum that goes from a very typical sharp taper tip, like in panel A, you see there, which is very typical for our idea of mode 1 deformation, all over more complex staircase tips where you clearly can puzzle back the host rock that has clearly just simply opened due to this intrusion, to bending of the host rock in between overlapping tips, all the way to blunt tips, which were not then placed in a clear fracture, but rather have lots of brittle, small-scale fractures around them. So while A would be a typical example of mode 1 deformation, F would be a typical example of a shear mode, mode 2 deformation. So in this case, we really find both examples of end member propagation in the same host rock, in the same circumstance, let's say. And we clearly saw that the control of local fracture networks, but also host rock strength from those more competent limestone banks to the less competent shales in between, but also those tip geometries, all of it played a role in the emplacement process, and we get more of a mixed mode, a more mixed mode image of or mechanism of emplacement. And another thing we looked at is the overall profile shape of the intrusion along its length, and we measured the half-width thicknesses, as you see on the left plot, and then compared it to what would be expected for a simple typical elastic fracture, which is this dotted parabol-shaped line. And you see that our half-width profiles don't correspond really very well to that typical shape. They rather very quickly increase from the tips away in thickness, and then their thickness remains rather equal across the intrusion. And this is on a small scale, but similar things are actually found across scales. On the right side is an image, a diagram from Toby Schmiedel and colleagues that was just recently published. And there they involve our data on the small scale, but also larger scale dikes from Argentina, and actually see that indeed we have those variations of shapes and those shapes that depart from a typical ellipse shape, sharp ellipse shape expected from mode 1 fractures. And we get a mixture. Even on those larger scales, we are seeing those very equal thickness dikes with blunt tips. So across a range of scales, across a range of viscosities, we see those similar indicators of non-elastic emplacement. But one thing that that makes all of us thinking, and I know we are all aware of it, is when we go in the field, when we look at those eroded plumbing systems of volcanoes, we are looking at the very final image, the moment when the very final drop of molten magma solidified into history, into geological history, and we have the final image only of a dynamic process. And recent work by Tara Stevens and colleagues in Scotland, I hope I'm right to say it was the Isle of Mull, where they observed, they quantified in detail the geometry of lots of overlapping cross-cutting magma sheets, and saw that I came up with this model that thinks actually about time as well, where they think in this location, most of the fractures started off as mode 1 fractures, so sharp tips, and then because of cooling, because of brecciation or of the host rock or pressurization, because of breaking through solidified fronts, etc. You then move from that very simple opening mode 1 magma sheet into more complex mode 2 deformation, with shear mode deformation, with blunt tips, etc. And I think this is a very important evolution, where we start thinking really about time when we look at the outcrops, where we try to disentangle the final state from the initial state. Sadly enough, most of the outcrops only preserve that final result, and the initial phase of deformation, of propagation, is lost, overprinted. So if geology has that limitations, then we probably have to go back to numerical models. And here are two examples. On the left side, Alban Souche and colleagues in Olivier Galland's group, they induced perturbations, isotropic and anisotropic, in a finite element model ahead of a blunt tip, and saw that by inducing those perturbations, so as an analog for layering, for fracturing in a host rock, we can move into shear mode deformation and more complex deformation. And a paper that was coupled to Tara Stevens' paper in Volcanica, and which I assisted in, simply took different geometries of a pressurized intrusion tip in a finite element model, and saw that just by varying that geometry of that tip, we can move from opening mode, mode 1, deformation of a host rock, into shear mode deformation, mode 2 deformation. And that's just by varying the geometry of the tip, or by working with host rock heterogeneities. So I guess what I'm trying to say is that we really need to take into account local context, local geological context when we think about our models. And therein lies possibly a danger with applying a more simple, elastic approach to any situation we have at hand. So we have geology and numerical models, but lab experiments have been used as a testing ground for a long time, for several decades now. And of course, one of the reasons is we can go ahead and test assumptions in a lab environment. So if we take that analytical assumption of elastic deformation, here in this case, again, a dike with a bulges and trough-shaped uplift at the surface. Well, if we indeed assume the Earth's crust will be elastic, we can use gelatine. Gelatine is transparent, so we can follow the evolution of an intrusion like we never really can in the field. And a dike, water dike, for example, injected in gelatine indeed forms that bulges and trough-shaped uplift at the surface. If we do the same with oil dike, for example, in granular material, we rather get a dome-shaped uplift, so that bulges and trough pattern disappears, and we only are left with a dome-shaped uplift that might become a bit more asymmetric when the intrusion tip moves close to the experimental surface, but still it's a dome-shaped uplift. So there's a mismatch here because the overall geometry of the underlying intrusion is similar, but the rheology of the host is fundamentally different, and we get fundamentally different surface displacements. So to have a better look at that, I also ran my own experiments. But first of all, we need to understand really the rheology of the materials we work with. And we did not feel like that was the case for the granular materials or mixtures we use. And coarse-grained sand mixtures with fine-grained plaster is a very typical thing used in analog experiments in volcanology. And we had a whole range of tests on that, and saw that if we increase the plaster content, indeed we get strength increase, cohesion increases, tensile strength. But in mechanical tests, ring shear tests, where we measure the shear stress on a sheared sample, we see that both as we increase plaster content in our granular mixtures, but also as we increase the normal load on the sample, we move from a typical brittle deformation with an initial peak at failure to a more broadly distributed deformation with no peak, that is rather plastic deformation. And that increase in normal load is similar to an increase in depth in our box, or actually analog to an increase in depth in the crust. So what we basically documented here is how with those granular materials, we can move across the brittle, ductile or brittle plastic transition in the crust, name it as you please. And so we really have a realistic material here to model crustal deformation. And by reconstructing failure envelopes with tensile and direct shear tests, again, details are in a paper in Tectonophysics published earlier this year, we could constrain cohesion and friction coefficient for a whole range of those granular mixtures. And in this way, we can use host rock strength now really as a variable, as an experimental variable. And as a little caveat, why do I think it's so important to go ahead and quantify in detail our analog materials before moving on? Well, we did a study in Brussels led by Pablo Grosse, where Pablo deposited cones, growing cones above strike slip faults in an experiment. And he used a funnel to deposit incremental volumes of granular material on his cones, but a mixture of 10% plaster with 90% sand didn't flow through the funnel as we would have liked. So he replaced the plaster with kaolin clay, with dry kaolin clay particles. And the stuff moved much better through the funnel, so we went ahead. And it's only afterwards when he calculated the slopes of those cones, as you see here, and used that as input for his experimental phase diagram you see on the right. And we realized those slopes were typically lower than the ones from previous experimental studies, and some of the structures in the experiments were not as clear as they could have been expected. And we then ran all of the mechanical tests we also did on the sand and plaster and realized the friction of such a mixture of kaolin clay with sand is obviously, because it's clay, much lower, and therefore the slopes of those cones were lower as well. So we made it work in the end and adapted the scaling, no problem, but really having a good hold on the rheology of our materials, both in our experiments, but probably also in the numerical models, is key here. And as I moved into my PhD, Eleonora's 2015 review came out and had this one line in the conclusion that caught my eye, because it summarizes what my thesis was going to be about. She wrote, "The single most important development that could drastically change the way we model dikes, I'm going to say magma sheets, is to move into 3D. And I couldn't agree with that more, because there was something lacking from granular experiments, at least. So we went ahead and developed a 4D monitoring method where we take our sandbox and place it into an X-ray CT scanner. And this helps visualizing the analog intrusions. So we have a CT scanner that continuously images 16 centimeters of the sandbox, and we get a whole time series of images, 3D images during intrusion of our golden syrup, which is our magma analog. It's all in a 2019 Frontiers in Earth Science paper. That's where you can find the details. We then use digital volume correlation, which is the 3D variant of digital image correlation, to quantify 3D displacements and strains. And here is what we found. So first of all, this is a low strength material, 10% plaster. And what you see forming here in the CT scans is a rather bulbous mass, let's call it a cryptodome, which with the dome-shaped uplift, and finally a magma finger that shoots through the surface and produces the rupture. And this is the time for your 3D glasses, if you have them, where you can see, if I turn this, and probably even without glasses, this gives you an idea of the 3D shape. So on my screen, this works. You get this bulbous mass with that magmatic finger. So here we can really follow in 3D the development of our modeled intrusion. And if we go on, if we then move to use all the same parameters, but in a high strength material, we follow a completely different intrusion geometry. We form a thin sheet that shoots straight to the surface, and notice how in the later phase, a surface fracture opens and propagates downwards to meet the magma somewhere halfway. And I will come back on that observation later. In 3D, again, if you have those glasses, go ahead. This shape is fundamentally different. It's a complex of thin sheets instead. I'll just let that turn till the end. So these are all nice images, but of course the DVC makes us quantify the deformation these intrusions cause really. And for the cryptodome on the left side, we saw rather shear mode deformation with those maximum shear strains concentrated around that intrusion, and then later on as the finger moved upwards, while for the dike, we rather see opening mode fracturing, where those arrows that denote displacement are rather pointed outwards than upward. So just by varying that whole stroke strength, we can move from one propagation mode into the other, which links with the geology we've discussed before. And so after all of this, my train of thought brought me to this question. How accurate are the inversion models really, where they assume linearly elastic deformation in those conditions where clearly the geology dictates that the deformation is dominantly non-elastic? And a natural example of that doubt, let's say, is Piton-La Fournaise. At Piton-La Fournaise, on the left side here, you see a map of the volcano. You have the Dolomieu crater in the center, which is essentially a pit crater connected by a ring fault to the shallow magma reservoir. Most of the seismicity measured on the volcano during active phases, and recently that's kind of all the time, let's be honest, most of that seismicity is concentrated along the ring fault and around that reservoir. When finally magma gets on the move away from that magma reservoir, then often it is aseismically, or there's only low seismicity, or there's some seismicity closer to the actual rupture and eruption site, but the path is not really highlighted by lots of seismicity. Why is that? Is that maybe because Piton-La Fournaise is far from a homogeneous elastic rock mass, but rather a loose pile of scoria, fractured lava flows, etc. So a medium that is much more similar to our granular, to our sandboxes than to a gelatin model or an analytical elastic source. And then here on the right side, you see a solution from inversions by Smitherello and colleagues, where indeed we have to come up with certain geometries that are not always seeming very realistic to try to fit our elastic assumption and the surface displacement and that very scarce seismicity into something that resembles a magma propagation path. And Olivier Galland's group summarized that very well in this image, where you have a gelatin experiment surface deformation of a dike on the left and one in granular material on the right, formed by completely different propagation modes. The overall geometry of the intrusion is similar, but at the surface, that's a different story. We get completely different displacement. But if we would apply then an elastic inversion to the right one, we would probably end up with something like a sill. That would be the estimate. So how about that mismatch between elastic solutions and plastic deformation? Well, here is another example of Owen Holohan and colleagues, where they used analytical elastic solutions of surface displacement that was produced by the depletion or depressurizing of an underground cavity in a distinct element method model, the DM model. This model allows plastic deformation, fracturing, shear mode fracturing, etc. It's basically a box of numerical balls, if you want. And what they saw is that as that cavity depleted and ring fractures, collapse fractures, and faults formed above that cavity, the elastic analytical solution actually became more and more shallow and rotated until it neared the surface. And in a volcano monitoring situation, we would estimate magma is on the move to the surface, while it's actually just an underground cavity that is depleting. So this clearly showed the mismatch. And we then thought, how can we further assess the accuracy of elastic inversion tools in clearly non-elastic conditions? Well, let's try to apply them to those sandbox experiments. And here is a near vertical dike or steeply inclined sheet, if you want. This is a rendered geometry, this red sheet here from an X-ray CT image. And using DVC, we can extract the surface displacement, vertical component, east-west and north-south, just as can be done nowadays from satellite interferometry data. And we then applied a very simple Okada tensile dislocation model to it. And this is a forward model where we take the exact intrusion parameters as we know them from the experiments, from the CT scans, and we run a forward model. In the left column, you have those observed displacements from the experiments, and then the modeled one, if we use our intrusion parameters. I think it's pretty clear that the model doesn't capture at all or estimates properly the displacement from that intrusion, and we get misfits and errors of which most geodesists would very fastly run away from. So we then moved on and did a unconstrained inversion where we just feed the data into the inversion and then see what it comes up with. And in orientation, depth, etc., it produces an apparent better fit, but it's still far away from what we know the intrusion is. In this case, we had a problem with the north-south component, but we are now in the course of fixing one after the other parameter, and here's an example of fixing the strike only. If we can assume that we know where an eruptive fissure surfaced, for example, we can fix that and then invert for the rest. And like this, we are slowly moving to a better fit and trying to see which parameters are more or less sensitive to that assumption, elastic assumption versus the plastic reality in our sandbox. So with all of that, I come to the final question: how can we reconcile models with geology? I won't claim I have the answer. In 2019, there was the LASI conference where Olivier Galland took us to those outcrops where they described viscous indenters and shear mode deformation. And standing in front of the outcrop, this outcrop, for example, that they described, indeed, there's shear mode fracturing, imbrication, etc. But that whole outcrop is confined by a thicker dike, a thicker sill. So are we looking at a very local feature here? And in many examples, we see that there is complex interaction between different intrusion segments because we're again looking at the final frozen state. So is this all local, local deformation, local processes that maybe don't matter for the broader scale deformation signal that is picked up by satellites? And can we just forget about that? Forget about those complexities in the numerical models, or should we really care? And should we try to build in more complexities in the commonly used tools for volcano monitoring? That's really a question that I hope to answer towards the future, or that we can discuss now. And so we wrote a review paper in the special issue that is upcoming, and it's in review now, on the past and the next decade of volcanology, focusing on analog models here, where we identified 3 fronts, and the third one would really be integrating analog and numerical models, and I would add geology into that. And benchmarking exercises, comparing different models could really help. And so in this way, I think by a multidisciplinary solution where we bring in elements from different sites, try to validate our numerical models and in various ways, is really an exciting front to continue on. And it's one thing we are doing now here in Warsaw by trying to build more complex numerical models or applications, at least, in the Demo Planet project, and trying to see if really that non-elastic deformation matters or maybe not. And hopefully in a few years, we will be able to answer that a bit better. But I think it's an important question for volcano monitoring efforts to understand how large the accuracies or inaccuracies of the models we use broadly really are. All right, thanks a lot. And I'm looking forward to discuss.
Thanks a lot, Sam. So we're taking questions now. If anyone has a question, you can type an X in the chat and I'll give you the floor, or you can just pick up if nobody wants to type an X. Or I can start questioning you, because I of course, this talk has been very interesting and a lot of interesting points to talk about. So I see that Janine has a question. So let's have her start and then I come afterwards. Go ahead, Janine.
Yeah, thank you, Chiara. Sam, that was fantastic talk. Thank you so much. It was really very clear and really nice to see lots of different lines of evidence coming together, and the fact that there's still a lot of discussion to be had. I guess my question is, yeah, it's more of a kind of discussion point really, rather than well, anyway, it's, you know, you're focusing a lot on in the natural system when magma is moving real time, on the ground deformation patterns that are created, and how in volcano monitoring they might be interpreted. And I think you make a clear point that actually there could be several different viable models which could create that source. Mm-hmm. But I kind of wondered on other kinds of information that are available when magma is moving, such as, for example, seismicity. You kind of pointed at that in a couple of examples at the start as a big source of information. So I wondered how the seismicity that is created as magma is moving, how is that, or do you have any observations on how that is recorded in the rock record when we go in the field? So do you know what I mean? Like, yeah. There could be some related to lots of different processes, and I think if for some volcano observatories, you know, seismometers are a big tool for them. So I'm wondering how things link together.
Yeah. Well, I'm clearly still completely immersed in that train of thought, because there's a lot of elements missing from that talk, and I was making the PowerPoint and saying, no, still that, oh no, this, and then I had to say, no, stop, because you're going to take it too far. I think I was already on the edge of an information overload here. So seismicity, petrology, all of these things have to be brought in. As for the seismicity, I think as we move to ever more dense, more detailed seismic networks, seismic studies, patterns start to emerge, right? And the best example I know of right now is the Bardarbunga intrusion, and I can't wait to see the data from this year's intrusion, because from what I've heard from others, there's again a lot to learn. But in that case, what people have seen is different mechanisms of seismic mechanisms that indicate shear mode deformation, or where existing faults tectonic faults have been reactivated, and the magma intrusion kind of exploiting existing weaknesses in a way of choosing preferential orientations of fractures and faults to reactivate. There's some nice studies by Torbjörg Augustsdottir, which really give a very good clue of how that has worked, at least in this case, because another thing I haven't even touched upon is far-field stresses, extension, compression, tectonic stresses that way, because often they are discarded as long-term states of stress that we probably don't have to care about when looking at hours or days of magma intrusion. But I do think they can matter in understanding the whole complex image. So as we go into the field, I guess exactly having the broader tectonic understanding of the context of that intrusion, and then the more local, potentially documenting the more locally reacted structures, faults, fractures, etc., trying to discern pre-existing from magma-induced fractures, which is really a headbreaker. It's not straightforward to do that in the field. So we need more of those studies, I think. And all in the end, they will definitely serve better interpreting seismic signals from ongoing crisis events.
That's great. Thank you very much, Sam.
Yeah.
All right, so thanks, Sam. Caitlin Chart now has a question for you.
Hi, thanks for a really great talk. It was so informative. I learned loads. I was just wondering about the effects of the fluid dynamics inside the intrusions and whether these would be like more or less significant in the elastic and plastic models.
Yeah, fluid dynamics, that's again another thing. Janine ran a very interesting set of experiments, gelatin experiments, where she visualized the flow patterns going on within her dikes, right? And again, from geology, looking in the field, it's clear it's a complex image, because using AMS, we can get an idea of that final frozen state of flow, if you want, within an intrusion, but again, it's the final state. So we don't know a whole lot about that. And I myself have not been trying to model. I can't image the flow dynamics really within the CT experiments, and I haven't had any touch on numerical models, so I'm not sure in how much. Obviously, viscosity, etc., it's all going to matter and time-dependent viscosity changes because of cooling, etc., are going to matter, and it's one of the conclusions of Tara in that complex evolutionary plot that she showed. As the magma cools and viscosity increases, you're more likely to move from that sharp tip to that more blunt tip, of course. So it's a complex interplay, and I'm not sure our analog models at least can provide a very good answer on that. But
okay, thank you.
Yeah.
Yes, following up on this, I think it's all very much interlinked. You know, you have a very complex rheology of the crust, you have a very complex fluid dynamics within the magma. So yeah, as you were mentioning earlier, Sam, I think the real question is, what are the first order processes that we need to tackle? Because we cannot do everything in one way. So we kind of need to find a way to split the problems in smaller and maybe easier tasks to begin with, and then try and put results together in order to understand what is the first thing that we need to look at. Yeah. Because as you say, the approximations are usually very big, and this problem fits also into the different scales that we're looking at, as you were mentioning earlier as well. So do we need to really care about the small scales when we have systems that are kilometers wide?
Yeah.
And if so, how do we deal with that in terms of modeling, for example, because it's complicated, because you can't do all scales all together. So yeah, I mean, a lot of interesting things to think about.
Yeah, this matter of scale is really a head wrapper, right? And yeah, probably like you say, attacking one by another. It's how we have been doing analog experiments for decades now, right? We know this complexity exists, but for the matter of this experiment, we ignore that aspect, then we focus on another aspect. And as we move on, we can bring some complexities together, but I don't think for some we are there yet. For example, the distinct elements, we are still not able to inject a thin magmatic sheet into that. So we first need to get those initial steps right before we can start comparing models, etc. Yeah, sure enough. As I said, it's still a question mark.
Absolutely. Yeah.
Definitely.
Yeah.
Yeah.
And lastly, I wanted to say another thing that you also touched upon, that is that we now have so many data sets and so good data sets that we might want to, start looking at things in a more, let's say, statistical and data-based approach.
Mm-hmm.
I think this might help us in realizing, what are the first order things that we need to look at, and what are the things that we can at least begin with forget.
Yeah, sure enough. Yeah, and by trying to apply the methods that are applied on real volcano monitoring data streams, on numerical model results, on analog model results, we can. I think there's a lot of power in doing that, in benchmarking, and we probably don't do enough of that right now.
Absolutely agree with you on that.
Yeah.
We have another couple of questions. One is from Gareth Fabro, and he's asking, how do the geological complexities change the critical stress we use to estimate when magma chambers will fail and the dike will start to ascend towards the surface? This is from Discord. Did you understand, Sam? Do you want me to?
Yeah. I think so. Gareth, hi. Hi, Gareth. How? Well, the strength of the whole stroke, its state clearly matters a lot, and many numerical models have shown that. I didn't even talk about viscoelastic models, for example, that try to take into account heat effects, etc. But also a major problem that is known, and I saw Mike Heap is on the talk here somewhere. He's working on how do we can measure the strength of a rock in the lab on a small sample, but how do we then translate that to crustal scale strengths? It's not so clear yet, and we still don't have all the tools. But we do know from experiments, I hope my experiments in combination with what Eleonora showed past time on gelatin experiments show that just playing with the rheology and the strength of those mediums clearly plays a role in propagation modes, etc. We can flip from one to the other. So the challenge then really is to kind of know the context of the volcano you're studying, and as good as possible, but still maybe indeed, like Chiara said at some point, admit that we don't need to care about all complexities to get an understanding of the system that is enough for hazard mitigation purposes.
Mike Heap has a question that is related to what you were talking about. Mike, do you want to go ahead and ask it, or shall I read it? Okay, I'll read it. He's asking.
Hi, Mike. Mike is here.
Yeah.
Hello. It's a question I guess we've discussed before, but as a rock squasher, it's interesting for people like me to know what is useful to measure for for people like yourself. And that includes the problem with the fact that our samples are very small, and you're dealing with problems that are very big. And so what should I be measuring in the lab? It'd be interesting to hear your thoughts on this.
Well, yeah, we've clearly discussed it, because Mike is now a collaborator in my current project. So it's not always a straightforward answer, I guess. One thing we realized in our analog experiments is that no one bothered about the tensile strength of those granular materials, for example. So then going further, knowing tensile strengths of rocks, but also importantly, how that changes with alteration would be important. Next to, of course, someone like Janine working with gelatin experiments definitely is interested in elastic properties of the rocks, something we simply cannot quantify on the granular materials right now, or at least not that I know of yet. Maybe some people have other thoughts. Not directly, but I guess that's part of the question, and yeah, definitely talking to each other would definitely be or continuing the conversation is definitely important in multidisciplinary teams. And I think that's a really good thing in our community. At least recently, we are really aware of trying to build those multidisciplinary consortia to tackle the problem instead of all working on our little islands. So part of my talk could have been in the past tense also, because we are aware of how we can move forward, I think, and that's exciting.
We have another question from Igor Collins, I think, and he's asking in the chat, do you simulate physical models to obtain your numerical results? If yes, I would like to know which physical model you use. Thanks a lot.
So in my current project, we just focus on numerical experiments, but the next step would be to exactly then plug in analog experiments also. The best example, I think, of that combination is what Eleonora and her group are doing. And she presented at Pastime. They use the gelatin experiments, repeated injection there, to validate inversion tools for estimating surface rupture. So I definitely advise you to go look at that, because I think that is the example that is at the forefront of how we can really use analog models as a powerful tool for informing numerical models, more than just comparing their outcomes. Because analog models can do things numerical models can't, and the other way around. In analog models, we somehow allow more degrees of uncertainty and can work with less assumptions, while numerical models still will be driven by the assumptions we use to build them. So while numerical models, we can probably, at least for some applications, run many more of them than we can during one day of lab work. So there's power to both. Yeah.
Thanks. Luca has a question now.
Sam, thanks for the interesting presentation. I was wondering, we are evolving toward models of very complex plumbing system with a lot of partially crystallized, compressible magmas everywhere through the crust in some cases. And I was wondering, then you go toward the top of the system and you have elastic material probably inside an hydrothermal system that can be altered. And I wonder, how much are we able to look through a magmatic system using surface deformation signal if this is very biased perhaps by the reaction of the surface deformation being controlled perhaps just by the top of the magmatic system, and there are a bunch of processes for which we are completely blind. Would you comment on this?
Yeah, it's one of the reasons, I guess, why I've always been so excited about using X-ray CT, because we can look below the surface where we can't with volcanoes. But I guess part of your question was answered by Janine, in the sense that exactly by using different geophysical streams, we have seismicity, we have
yeah, but which one? Because
all of them.
Yeah,
all
no,
of
but
them.
I see what I mean. What you mean, but it's obviously the multidisciplinarity is a solution to many things. But I wonder if we have to recognize that there are some things we will never see, and then we need to look for solution. For instance, if you are in the middle of a marsh, very compressible, are we ever going to see the intrusion of a small volume of magma inside something very compressible, or at I don't know, at 20 kilometers
maybe not
depth?
Yeah, obviously, yeah, there's limits to our techniques we have.
So one thing
sure.
I would find very interesting is to find the limits, a bit on the line of what Chiara was saying. What can we do, and what? So it's the thing of we know what we know, we don't know, and all these things. But it's really about that. I think there is a part of the things that as a community we should do, and say, look, here we cannot do anything. We are totally blind. And I think it would be good, because perhaps we have different blind points, but maybe on the overlap we can cut off a little bit of the blind points and resolve some issues by seeing what we cannot do really, or for the moment we cannot do, hopefully.
Yeah. So in our little review for Bulvolk, we identified one of 3 fronts that I think is more broadly applicable, where exactly benchmarking, but also community workshops where you just throw everything you have at one single volcano can really help detect some of those overlaps, but also gaps, right? And we just have to keep pushing forward as much as we can with quantifying our experiments as properly as we can, understanding the vulnerabilities of our numerical models, etc. So that was a bit the idea of that inversion exercise we did with my experimental data. I've had people saying, "Oh yeah, but actually, I mean, your material is not elastic, so it's irrelevant what you're doing." But we just hope to shed some light on the uncertainties or vulnerabilities of that model. And of course, we are going to move into trying to apply more complex, or at least distributed opening, maybe finite element models, etc., to go further in that. But it's a useful data set that can help at least comparing the numerical tools.
I just wanted to say bye. I need to grab some lunch and then I'm teaching. So thanks a lot again.
Right. Thank you very much. In any case.
Bye-bye.
Yeah.
Okay. I don't see any other questions here. Correct me if I'm wrong. Otherwise, I think we can more or less call it a day. Karin, did you want to say something regarding ECRs?
Yeah, so if there's any ECR folks who are still on, we're going to try set up a monthly coffee time starting, yes, Sam, starting in 2022. So on January 6th, we'll have our first one. We're going to do it on GatherTown. So there's the link to it there, which you can also find on Discord, and we'll send an email out later on this month. Additionally, we're working on a form, so ECRs can, if they're interested in sharing or convening a sessions, can kind of sign up for that, so that we have a resource of people we can reach out to, so that ECRs can get more opportunities to do some other stuff in our community. Yeah, that's it.
Yeah. Thanks a lot. Thanks everyone, especially thanks Sam for a very interesting seminar and discussion.
Thank you.
Oh,
there is one more question here.
Yeah, there's a final question. So where do magma chambers form in the Earth? Because in the literature, many authors use cylindrical conduits to model ascent, and for myself, I can't imagine a duct so long.
We probably all have some answers that might be different to this question. So I guess I have the honor of going first. Again, all depends on context, right? We clearly are moving away from the idea of a simple magma chamber, a cylinder or an ellipsoid in the subsurface that feeds eruptions. Magma plumbing systems are complex systems with layered intrusions, with layers of intrusions spread throughout the crust. You have mush, etc. So, and the magma, the eruptible magma sits somewhere in between. So, so there's no, I think, simple answer to that question. Neutral buoyancy is an fundamental idea that where you can start from, but then context plays in as much role, and probably half of the people are shaking their heads like this when I say neutral buoyancy anyway, because it's so much more complex than only that. But in your models, you just have to use some assumptions and roll with them, as long as you realize what they are. And there's no choice for us, I think. I don't know if that was an answer, probably not, because, yeah.
Yeah, I think it was a good answer anyway, so thanks again. Yeah, thanks again, Sam. Thanks everyone for participating. And thanks to the VIPS Commission for organizing this. Enjoy your afternoon and see you all soon, hopefully.
Yeah, likewise, and thanks so much for the invitation.
Thanks, everyone. Bye-bye.
Bye.
Bye-bye, thank you.
Bye, thank you.